learners for this course on control engineering. In this final module, that is in module 5, we were discussing on bode plot, that is stability analysis using bode plot. We have already solved 3 numerical problems on bode plot. In today's lecture, let us continue our discussion. The problem number 4 on stability analysis using bode plot states that sketch the bode plot for the following transfer function and determine the system gain k. For the gain crossover frequency omega gc to be 5 radians per second. Whereas the open loop transfer function, that is g of s h of s, is given as k e to the power of minus 0.1 s divided by s of s plus 1 into 1 plus 0.1 s. Come, let us find the value of k, for which the gain crossover frequency must be 5 radians per second, and moreover he is asking us to plot the bode curve, bode attenuation curve. Now, if I observe the problem, the one more additional term can be seen in the numerator of this open loop transfer function, that is e to the power of minus 0.1 s. So this term is nothing but time delay factor. Kindly make a note of it. This is called as time delay factor. How to analyze this time delay factor? What is the effect of time delay factor on magnitude plot as well as on angle plot? Let us discuss those things also. So if I move for solution of this problem number 4 of our discussion on bode plot, as usual in step 1 I should write this in standard time constant form. Obtain standard time constant form is the step 1. So if you observe the given problem itself in standard time constant. What is standard time constant form? The standard time constant form is g of s into h of s. So since he has not mentioned h of s, we can take h of s as unity. This is a unity feedback system, we can consider it like that. And the standard form is what? K of s to the power of m, that is number of zeros at origin into 1 plus tas into 1 plus 2 zeta omega n s plus s by omega n whole square. So this is a standard time constant form for zeros. Whereas for poles it is s to the power of n 1 plus t1s 1 plus 2 zeta omega n s plus s by omega n square. So this is a time constant form for poles. So this is constant k, this is number of zeros at origin, this is simple 0, this is complex 0. This term is called number of poles at origin. This is simple pole, this is complex pole. These two people already know. Now we compare the standard time constant form to the given question and get the standard time constant form. If I carefully observe, for simple poles and zeros, it should be 1 plus ts form. E itself has been given itself in 1 plus ts form. No worries. And we don't have any zeros for this problem, but we have one pole at origin. So one pole at origin, simple pole, and time constant k. In addition, we have the time delay factor e to the power of minus 0.1 s. So therefore, no need to worry, write it as it is. So given problem itself is in standard time constant form, k into e to the power of minus 0.1 s divided by s of 1 plus s into 1 plus 0.1 s. Now, if I move for step 2, that is discussion of various factors. If I move for step 2, discussion of various factors. Discussion of various factors. First one is constant k. Here, the constant k itself is unknown. We should determine what is the value of k for gain crossover frequency of 5 radians per second. Hence, k itself is unknown. K itself is unknown. I should find it. In order to find that, the entire magnitude plot should be shifted by an amount 20 log 10k. These two people already learned. Let me do that when I go for bode attenuation plot. Next, move for the second one. What is the second one? That is time delay factor, that is e to the power of minus 0.1 s. So this is a new factor which you have not at all encountered in this module. Now, What is the effect of e to the power of minus 0.1s on magnitude plot and on phase angle plot is the question to be answered. In order to analyze that, let us take it in rectangular form, that is a plus ib form. For that, replace s by j omega. Replace s by j omega. It is nothing but I omega. J is nothing but imaginary times omega. If I do that, it will be minus 0.1 j omega. This is of the form e to the power of I theta. This is of the form e to the power of I theta, which can be written as cos theta plus I sin theta, correct? So now it is of the form e to the power of minus I theta. What is e to the power of minus I theta? Cos theta, that is cos of theta value is 0.1 omega cos theta minus j sin theta. J sin theta is 0.1 omega. So cos theta minus I sin theta is the value of e to the power of minus I theta, where theta is 0.1 omega. Now from this I can easily calculate magnitude as well as phase angle. How to find magnitude? So magnitude, that is modulus of e to the power of minus 0.1 s is nothing but root of a square plus b square. What is root of a square plus b square? It is root of cos square 0.1 omega plus sin square 0.1 omega. Cos square theta plus sin square theta is 1, correct? So cos square theta plus sin square theta is 1. This is in terms of what? Linear scale, correct? But I want it in logarithmic scale because the bode plot is a semi-log plot where x-axis is logarithms whereas y-axis is linear scale. So therefore I want the magnitude in log scale. So therefore in log scale this is nothing but modulus of e to the power of minus 0.1 s is equal to 20 log 10 of magnitude. Magnitude is 1, which is equal to 0 decibels in log scale. So since it is 0 decibels, this does not have any effect on magnitude plot. This does not have any effect on magnitude plot. So it is 0 decibels, hence it does not have any effect on magnitude plot. So it does not have any effect on magnitude plot. No worries. What about its effect on phase angle plot? So for that we know phase angle. That is also a very important parameter, right? So for phase angle, we know that phase angle is given by angle of e to the power of minus 0.1 j omega, which is nothing but tan inverse of imaginary part by real part. What is imaginary part? Imaginary part is minus sin of 0.1 omega, imaginary part by real part. Real part is cos of 0.1 omega. Now sin theta by cos theta is tan theta, which is nothing but tan inverse of tan of 0.1 omega. Tan inverse of tan of 0.1 omega. So tan inverse into tan will get cancelled. Hence the angle will be 0.1 omega radians. Because we know that whenever we write it in e to the power of I theta form, theta will be always in radians. So therefore here theta will be in radians. In degrees, the angle will be how much? So phase angle of e to the power of minus 0.1 j omega will be what? In degrees, it is 0.1 omega. But here we have minus, so it should be minus. Don't forget to put the sign minus, hence this will become minus. Don't forget the negative sign because it is of the form e to the power of minus I theta. That's why you are getting the negative sign, minus. So here also you should get minus. into, this is in radians, I want it in degrees, that is 180 by pi degrees. So therefore in degrees it will be minus 0.1 into 180 by pi degrees. So in degrees it will be minus 5.7296 omega degrees. So what is the phase angle effect? The phase angle effect is minus 5.7296 omega degrees. So there is no effect on magnitude plot, but there is an effect on phase angle plot. This we should consider when we calculate phase angle. Hope you follow. Next, move for the third term. That is, third term is one pole at origin. One pole at origin. That is 1 by s. 1 by s term. We know that for 1 by s term, it is a straight line with slope. Straight line with slope of, what is the contribution? Minus 20 dB per decade. Slope minus 20 dB per decade. Minus 20 dB per decade. For omega greater than 0, that we already know. 20 dB per decade at omega crossover is greater than or equal to 0. Now move for the fourth term. So if we move for the fourth term, the fourth term is first simple pole. When we consider 1 by s, if I consider 1 by s, it is nothing but simple pole. The contribution of simple pole is also minus 20 dB per decade, because this is inverse. Pole is written as what? 1 by 1 plus s. If I write as 1 plus s, it is simple 0, correct? But here what we have is 1 divided by 1 plus s. That is simple pole. So for simple pole, don't forget to write this inverse, otherwise this means 0. Simple 0. If I write inverse, then it is called as simple pole. Now for simple pole, if I solve, we already know that it is a straight line plot. It is a straight line with slope minus 20 dB decibels per decade at, what is the corner frequency? Here the value of time is 1, correct? 1 plus Ts form, if I consider coefficient of s is unity, hence the time period t is also 1, omega will also become 1. Omega c greater than or equal to unity, because time is 1 seconds and omega c is equal to 1 by t, that is also equal to 1 radians per second. Next, move for the fifth one, that is, fifth one is also simple pole. That simple pole is given by 1 plus 0.1 s. That is 1 divided by 1 plus 0.1 s can be written as 1 plus 0.1 s inverse. This is also a simple pole. Now, what is the contribution of simple pole? So for magnitude plot, it is also a straight line. It is also a straight line with slope. Straight line with slope minus 20 decibels per decade at, what is the corner frequency? So in order to find the corner frequency, we should know time period. Time period is 0.1 seconds, correct? Now omega is 1 by t, so omega will be 1 by 0.1, which is nothing but 10 radians per second, which is nothing but 10 radians per second, so greater than 10. Now let me use this space properly, because I want to go for phase angle plot also. So therefore what I will do, I will stop here and make use of this space for resultant, which is very, very important, correct? Let me neglect one column, that is factors. Directly will write the range of omega and resultant slope. That is what we require, right? Range of omega and resultant slopes to plot magnitude plot in bode attenuation. Now, coming for the first factor, that is k, it does not have any effect on magnitude plot. Only thing is that to find k, I should shift the entire magnitude plot by an amount 20 log 10k. That we will do later. Now, coming for the second term, this does not have any effect on magnitude plot. Leave it. Now, come for the third one. Third one is what? One pole at origin. So, range will be greater than 0, less than 1. Correct? So, from 0 to 1, the slope is minus 20 decibels. Now, from 1 to 10, we have simple pole. So, therefore, from 1 to 10, we have simple pole. Contribution of simple pole is minus 20. So, minus 20 will become minus 40 decibels. Now, above 10 till infinity, we have another simple pole. So, contribution of simple pole is also minus 20 dB per decade. Hence, minus 40 minus 20 leaves us minus 60 decibels per decade. So, all these are decibels per decade. It is not decibels, it is decibels per decade. These are slopes. You people already know what is the meaning of decade. We are considering only 3 factors because k factor does not have anything. The second factor, time delay factor, is also not have any effect on magnitude plot. Only we have effects on magnitude plot by one pole at origin and 2 simple poles. Considering which, from 0 to 1, I have minus 20 dB per decade. From 1 to 10, I have minus 40 decibels per decade. And from 10 to infinity frequency input, I have minus 60 decibels per decade. So, using which I should construct magnitude plot. So, I finished the analysis of magnitude plot. Now, moving ahead, that is phase angle plot in step 3. Step 2 is finished. Move for step 3. What is step 3? Step 3 is phase angle plot, correct? Step 3 is to find the phase angle. What are you going to do here? You are going to determine at what corner frequency the phase angle value is minus 180 degree, correct? That you know the trick how to determine the frequency without actually plotting the bode plot. Let us do that and identify at what frequency I am going to get minus 180 degree phase angle. That frequency is nothing but phase crossover frequency. Now to determine phase crossover frequency, first let us construct the equation for phase angle. Phi is equal to, so k factor does not have any effect on phase angle. Coming for the second term, time delay factor, it has effect, right? Its effect is minus 5.7296 omega. Minus 5.7296 omega. Time delay factor effect. Next, coming for one pole at origin. For one pole at origin, we already know that the effect is minus 90 degree. Minus 90 degree. Because for poles at origin, general expression for phase angle plot is minus 90 into n, where n is number of poles at origin. Whereas for magnitude plot, it is minus 20 decibels per second into n, where n is number of poles at origin. Whereas for zeros at origin, it is plus 90 into m, where m is number of zeros at origin. Whereas for magnitude plot for zeros at origin, it is plus 20 decibels per second into m. Correct? So done. Next, move for simple pole. For simple pole, how to get the phase angle? It is tan inverse of imaginary part by real part, for which I should replace s by j omega. So replace s by j omega. It is in the denominator. Hence, it is minus tan inverse of, replace s by j omega. Replace s by j omega. If I replace s by j omega, imaginary term will become omega, real term will become 1. So therefore it is minus tan inverse of imaginary part is omega, real part is 1, that is tan inverse of omega. That's it. Next, move for the next pole. It is also in denominator, correct? This is 1 divided by 1 plus 0.1s. So hence it is minus tan inverse of, replace s by j omega. The imaginary part will become j times 0.1 omega. So imaginary part is 0.1 omega. It is tan inverse of imaginary part is 0.1 omega divided by real part is 1. So done. I got phase angle equation now. Now without plotting the bode attenuation plot, I can determine what is the phase crossover frequency. What is the meaning of phase crossover frequency? The frequency at which the phase angle value is minus 180 degree is called phase crossover frequency. Now let us use the trick what I have explained to find what is the phase crossover frequency. Let me show that. That is, type the equation in alpha x form. I want the phase angle as minus 180 degree. I'll take this minus 90 to left hand side, it will become plus 90, which must be equal to minus 5.7296 into omega is what I should calculate, alpha x minus shift tan inverse of omega, that is alpha x again minus shift tan inverse of 0.1 omega, 0.1 into alpha x, bracket close, shift solve is equal to, and wait for the answer. I got the answer. The phase crossover frequency is 2.173. Hence I got the answer. The phase crossover frequency is 2.173. So therefore I can do the tabulation for the various values of omega. What is the value of phi? For various values of omega, what is the value of phi? For various values of omega, what is the value of phi? I know that the answer is 2.173 is the phase crossover frequency. Take few points after that and few points before that. Let me start from 0.1, 0.2, 0.5, 0.8, 1, 2, 3, 4, 5, 10, 50 and 100 if possible. Now if I do that, 100 is not required because I am getting the answer here itself. Take few points after that. It will go with 8, 10, 50. It will go with 8, 10 and 15. Now put these values of omega and find phi. That is minus 5.7296 into 0.1 minus 90 minus tan inverse of 0.1 minus tan inverse of 0.1 into 0.1. I'll get the answer as minus 97 degrees. So like this you complete this. So if I complete this, I'm going to get the answer as, for 15, I'll get the answer as minus 318 degrees. So where is the phase crossover frequency? It is between 2 and 3. And how much is the answer? 2.173. We have already calculated. So I have finished the tabulation for phase angle plot also. Now let us move for step number 4, that is bode attenuation plot, and find out what is the value of k for the gain crossover frequency as 5 radians per second. Come, let us quickly draw bode plot. Now moving ahead for step number 4, where in which I want to plot bode attenuation curve, for which the maximum resultant slope what I have is minus 60 decibels per decade, and the phase crossover frequency which we have already computed by using the alpha x technique from calculator. From the calculation it should be between 2 and 3, but the exact answer is turning out to be minus 180 plus 90. I'll take this to left hand side. Alpha is equal to minus 5.7296 into alpha x minus tan inverse of alpha x minus tan inverse of 0.1 into alpha x, shift solve is equal to. So if I solve, I am getting the phase crossover frequency as 2.173 radians per second. At 2.173 radians per second, the phase angle plot is crossing minus 180 degree. Now let us determine the value of k for gain crossover frequency to be 5 radians per second. So maximum is minus 60 slope which I require. So therefore I should start from plus 60. This you people already know. For negative slopes, I should use positive magnitudes. So for minus 60, I should use plus 60. So start the problem with 60, 40, 20, and then 0 decibels per decade, minus 20, and minus 40. That is enough. Now coming for angles. Angles are starting from minus 90. So therefore let me use minus 90 degree. 90 plus 30 is 120, plus 30 will be 150, plus 30 will be 180, plus 30 will be 210, plus 30 will be 240, plus 30 will be 270 degrees. Done. Now coming for frequency variation, it is varying from 0 to 1, 1 to 10, 10 to infinity. Let me use as usual scale, that is I'll start from 0.1 radians per second, multiples of 10. This is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and 10 to the power of 4. So this is frequency in radians per second. Frequency in radians per second. Clear? So now I want to generate the slopes. So slopes are generated by connecting 0 dB at 1 radians per second. So this is the point. 1 radian per second, 0 decibels. Connect the points to generate the slopes of minus 20, minus 40 and minus 60. So connecting which I am going to get the slopes of minus 20 decibels per decade, minus 40 decibels per decade, and minus 60 decibels per decade. Similarly, if I want positive values, connect minus 20 to here, you will get plus 20 decibels per decade. Connect minus 40 to here, you will get plus 40 decibels per decade line. So if I want negative slopes, use positive values. If I want positive slopes, use negative values of magnitude. Now reference for magnitude plot is 0 decibels. So at 0 decibels, you draw a dark line as a reference. Draw a dark line at 0 decibels for as a reference. And for phase angle plot, it is minus 180 degree. Draw at minus 180. Done. Now if you observe, the shift is not available. The shift is 20 log 10k. Here k itself is unknown. So therefore what I generated itself is the starting lines. So I should start from minus 20 decibels per decade from 0 to 1. It is already done. 0 to 1 minus 20 decibels per decade is already done since we don't have any shift. Next, minus 40 from 1 to 10. Minus 40 from 1 to 10. So therefore initially what I have itself is minus 20 decibels per decade from 0 to 1 radians per second. Let me leave some space so that you will understand that I have overlapped on the previously generated slope line itself. 0 to 1 I have done. Next from 1 to 10 it is minus 40. From 1 to 10 it is minus 40. So take parallel to minus 40 and extend it directly to 10. 10 is here, so therefore extend it to 10. Extend it to 10. Next, from 10 to infinity, I should use minus 60 decibels per decade. So for minus 60 decibels per decade, I should use from tend to infinity. Done. This completes the phase angle plot. This completes the magnitude plot. Coming for phase angle plot, we have at 0.1 minus 97, at 0.1 minus 97, at 0.2 minus 104, minus 104 will be here, at 0.3 minus 122, minus 122, at 0.5 minus 137, at 0.5 it is minus 137, at 1 it is minus 146, it is minus 146, at 2 it is minus 176, at 2 it is minus 176, 176, at 3 it is minus 195, at 3 it is minus 195, at 4 we have minus 221, at 4 radians per second we have minus 211, it's 211, at 5 we have minus 224, at 5 radians per second we have minus 224, 216, 222, 224, at 8 radians per second it is minus 257, at 8 radians per second it is minus 257, for 4 it is 211, this is 4 and this is 5, then 8, for 8 257, 240, 246, 252, 257, and for 10 it is 277. Done. Now draw smooth curve. Draw smooth curve. This will give you phase angle plot. So done. So I have plotted both magnitude plot as well as phase angle plot for the given values. Now according to our analysis, I am getting the phase crossover frequency for this problem to be 2.13, which we already know. Now what he is asking in the question, he is asking to find the value of k for gain crossover frequency to be 5 radians per second. Take 5 radians per second as the gain crossover frequency and find the value of k. So taking 5 radians per second as gain crossover frequency, it is here. This is 5 radians per second, correct? So take this as gain crossover frequency. Take this as gain crossover frequency, he says. Taking omega gc as 5, omega gc to be 5 radians per second. So this can only be possible if at 5 radians per second the magnitude plot value is 0 decibels, which means that I want the entire magnitude plot shift to be like this. The entire magnitude plot should shift like this. That is, the magnitude plot crosses 0 dB line at 5 radians per second. So I want shift like this. So such a shift is required to get 5 radians per second as the. So this is what we require to get 5 radians per second as gain crossover frequency. So for which the entire magnitude plot should shift from here till here. So how much is the shift? How much is this shift? The shift required is turning out to be 28 decibels is the shift required. The shift required is 28 decibels. If we shift the entire magnitude plot by 28 decibels, I'll get the gain crossover frequency as 5 radians per second. How do you obtain this shift? The shift is nothing but 20 log 10k, correct? So therefore, for omega gain crossover frequency to be 5 radians per second, the shift 20 log 10k must be equal to 28 decibels. Hence find the value of k. K can be written as what? Let me solve properly. It will become 28 by 20. So hence k is equal to 10 to the power of 28 by 20. .4. Hence I'll get the value of k. K is 25.12. The value of k for this problem is turning out to be 25.12. Or directly we can use alpha x method, that is 20 log alpha x, alpha is equal to 28, shift solve is equal to, I'll get the answer as k is equal to 25.12 itself. Let me complete the plot. That is, this is for the problem g of s is equal to k into e to the power of minus 0.1 s divided by s of 1 plus s 1 plus 0.1 s, and the scale for the problem will be, for y axis, for magnitude 1 unit is equal to 20 decibels, for phase angle 1 unit is equal to 30 degrees, and we have the axis marking like this. From this point till the beginning, it is magnitude in decibels, and from here till here it is phase angle in phi. So let me write it like this: magnitude in decibels, and from here we have phase angle in degrees. Phase angle in degrees. So this is what we had. And for 5 radians per second of gain crossover frequency, I got the value of k as 25.12. This is the complete solution for problem number 4, in which we have calculated the gain value of k, for which the system will be stable for the given gain crossover frequency of 5 radians per second. That's all from this lecture. Thank you all.